All right, let's dive in. Today, we're cracking the case on one of the most important processes in all of chemistry. We're going to frame it like a story, a thriller even, the Great Electron Heist, also known as redox reactions. You've probably heard the term redox before. It's short for reduction oxidation. And the crazy thing is, these reactions are happening literally everywhere, all the time. The battery that's powering the device you're watching this on, that apple on your counter turning brown, yep, that's them. They are the invisible architects of so much of our world hiding in plain sight. So, let's start with a little puzzle. What on earth could a crackling fire, a slowly rusting car, and a battery all possibly have in common? They seem totally different, right? Well, the answer is a tiny subatomic particle that's constantly on the move. And by the time we're done here, you'll see exactly how it all connects. To understand this heist, we have to start where every good investigation does, at the scene of the crime. Let's take a look at the first clues that chemists way back when first started to notice. A long time ago, the definition was really simple, something you could just see with your own eyes. Scientists saw that when things burned, like a piece of carbon, they were combining with oxygen, so they called that oxidation. Makes sense, right? And the reverse, taking oxygen away, they called reduction. It was all about what oxygen was doing. But here's the thing, that was just scratching the surface. They soon realized that all sorts of reactions that had absolutely nothing to do with oxygen were following the exact same patterns. There was something else going on, something deeper, a secret plot that was way more, well, electrifying. And this is where we uncover that secret plot. It turns out the real culprit wasn't oxygen at all. The real story, the modern story, is all about the transfer of electrons. This is the key that unlocks everything. And the secret code to understanding this whole thing is a super simple phrase. If you remember one thing today, make it this: oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Say it with me, oil rig. That little phrase is the absolute heart of every single redox reaction. And this shows it perfectly. Take a look. A regular old copper atom can ditch 2 electrons. That's a loss, right? So, oil. Oxidation is loss. Now, on the flip side, a copper ion, which is basically a copper atom that's already lost electrons, can grab 2 to become a neutral atom again. That's a gain. So, rig. Reduction is gain. Simple as that. Now, every good heist needs a crew, right? You need the one doing the stealing, and you need the one getting stolen from. In chemistry, we call them agents. So, let's meet the suspects responsible for this whole electron transfer business. Okay, stick with me here, because the names can feel a little backwards at first, but I promise they make total sense. The substance that loses electrons, the one that gets oxidized, is called the reducing agent. Now, why is that? Well, because by giving its electrons away, it causes the other substance to get reduced. See? And the opposite is true for the oxidizing agent. It's the electron thief. It gets reduced, but in the process, it causes the other guy to get oxidized. They're a team. You can't have one without the other. So we know electrons are on the move, but in a really complicated chemical reaction with a bunch of different players, it can get messy trying to figure out who's losing and who's gaining. For those tough cases, we need a special tool. We need a detective's toolkit. And that tool is called the oxidation number. You can just think of it as a little bookkeeping number, like a tracking device, that we assign to every single atom in a reaction. It's how we follow the money, or follow the electrons. Now, assigning these numbers might look scary, but it's really just a simple 4-step puzzle. Okay, step 1, any element just chilling by itself is 0. Easy. Step 2, a simple ion, its number is just its charge. Done. Step 3, this is the big one. Inside a compound, there's a pecking order. Fluorine is the king, it always gets -1. After that, you listen to hydrogen, who's usually +1, then oxygen, usually -2. And finally, step 4 is just the final check. All the numbers in a neutral compound have to add up to 0. For water, H2O, oxygen gets its -2. That means the 2 hydrogens have to be +1 each to make it all balance out to 0. See? It's just a little puzzle. So why do we bother with all that? Because of this. This is the big payoff. You just compare an atom's oxidation number before and after the reaction. If the number went up, it lost negative electrons, so it was oxidized. If the number went down, it gained negative electrons, so it was reduced. Boom. That's our foolproof method for cracking the case every single time. All right, detective, we've got the theory down, we've got our toolkit. Now it's time to see a heist happen right before our eyes. Let's check out the playbook for a real-life electron transfer. So, here's our scene. We have a simple rod of zinc metal, that's our suspect, and it's about to be dipped into a beaker filled with this bright blue copper sulfate solution. Now that blue color is key. That's the signature of copper ions just swimming around in the water, waiting. And watch this. As soon as the zinc touches the solution, the heist is on. The zinc atoms on the rod start giving away their electrons to those copper ions in the solution. The zinc is being oxidized, and the copper ions are being reduced. And you can literally see the evidence. A layer of reddish copper metal starts building up on the rod, and at the same time, the blue color in the solution starts to fade away.
And here we are at the end. The heist is complete. The blue color is totally gone because all those copper ions have accepted electrons and turned into solid copper metal, which is now plated all over the zinc rod. And where the zinc go? It lost its electrons and dissolved into the solution as zinc ions. A perfect visible electron transfer. Zinc was oxidized, copper was reduced. Case closed.
What we just saw was one specific play from the heist playbook. It's called a displacement reaction, where zinc basically pushed copper out of the solution. But these electron heists can be run in all sorts of different ways. Let's just take a quick peek at the gallery. You've got combination reactions, where two things team up to form something new. There's decomposition, where one big thing breaks apart. We just saw a displacement, the classic switcheroo. And then you get this really weird one called disproportionation. That's like an inside job, where one element in a compound is both the thief and the victim at the same time. It's wild. And this quote here really gets to the motivation behind the crime. In our example, zinc gave its electrons to copper. But why? This quote tells us it's all relative. The desire to gain or lose electrons completely depends on who your dance partner is. An atom might happily give away its electrons to one element, but turn around and fiercely steal them from another. Which leaves us with one last big question. We've seen the heist, we've identified the suspects, and we've tracked the loot. We know that electrons are stolen. But what is it deep down that makes one atom a master thief and another an easy target? Well, that's a story for another time.